Howdy and welcome to ECEN 215, Principles of Electrical Engineering. This is the final of lecture on DC nodal voltage circuit analysis. And this is just now taking what we have built upon so far, which is kind of introducing the actual method, showing the linear system of equations. And now we're going to do a little more examples of the process for doing nodal analysis. So let's go ahead and get started. So again, nodal circuit analysis, just as a review, is where we are taking a look at these individual nodes and we're using Kirchhoff's current law that states that all of the current entering this particular node, the sum of that current must equal to zero. Now, I like to do things, and you might be different. I've had several students like doing it different ways. Where I have a node, I like to use leaving current always. So the sum of all the currents leaving must equal zero. The reason I like that is because I can always start with the node that I'm on, subtract the other node, and get, V2 minus V3 over R3 gives me this current. It's a natural breakdown of that. I know that in some of the physics classes, I think they do it differently. And I've had some students that have preferred that method where you do everything entering, where you do this method, and that's perfectly fine as long as it's consistent. Um, if you try to do it in a different way, it'll end up confusing you, and especially if you're hopping back and forth with different methods in the same set of equations for all the different nodes, it will confuse you and make things worse. So just choose a method and stick with it. Like I said, I use leaving. That's the method I've used, and it seems to serve me well. So here we have three nodes and a reference node. And so we can write three sets of equations and then solve for that. So that's what we had the other day. So let's take a look at a particular problem. Let's look at a little bit more advanced problem. So problem 2.52 out of the book has this. Now the only problem with this problem that kind of makes it complicated is we've got this node here. So we'll call this node 1, V1. We can call this node 2, V2. Now notice I circled both of the dots because it's all one node. And then we have this right here, V3. So if you see this, I've seen students also will write an equation for this or V2, and then they'll write an equation for this separately. You don't need to do that. This is all shorted together. This is all one node because it's all about the elements that are connected together. This element is connected, this 5 ohm resistor is connected here, and this 20 ohm resistor is connected here, and it's all connected to this one node. Same thing with this 15 volt power supply. The only thing is with this particular problem that kind of makes it complicated is we have this 15 volt power supply. If it was a current supply, as is with this 1 and 2 amps, this would work really good for a KCL, but instead we have a power supply, which complicates things just a little bit. So let's go ahead and dive in on this problem and start sorting this out. So again, we'll just go ahead and call this our reference node, V1, V2, V3, and let's move on. So got the problem here. So let's write our first equation for V1. That's pretty straightforward. V1 over this 2 ohm resistor, so that is the current that is going through here. V1 minus V2 over 5 ohms, that is this current here going this way. I'll draw it a little cleaner for you. I'll admit I'm kind of old school. I'm used to doing this on a whiteboard. And then we have this 1 amp. Well, since this is actually going into the node, technically if we were writing this proper, we would say minus 1 equal to 0, but obviously that just slides over here and becomes just 1 amp. So that's where this equation comes from. So that is our first nodal equation. Now let's look at node for V2. Well, remember, this is KCL, so we got to look at currents. We're going to create this arbitrary current called I15V. meaning the current flowing through the 15-volt power supply from the negative. Now, I've arbitrarily chose the direction of the arrow. I chose it going through from the minus to the positive side, since this is a generating supply, which means, it's just a current. We don't know what the current is, but we have to assign it a variable, so we call it I15V. So I have V2 over 10 ohms, so that's this current right here. I have V2 minus V1 over 5 ohms, so this current right here. Then I have V2 minus V3, so that's this current. And all that's going to equal I15V. Since this current is coming in, the negative version is going out, so we just flip it onto this side, same as we did with the 1 amp. So that is equal to I15V. That's it. That is the equation for node 2. So what is the equation for node 3? Well, it's similar. We have this V2 or V3 minus V2, so this branch right here. Well, this time I15V is leaving this particular node, so plus I15V is equal to 2 amps. Since that's entering the node, we can put it on the other side of the equal sign, just like we've done with this other stuff. And those are our 3 node equations. Now, do we know something else? Yes, we do. First of all, we know the relationship between V2 and V3 because there's a power supply right here. So we're going to write that down in a second as well. But we also know that this is going to plug into this. I mean, I15V. We know what I15V is. I15V is this equation. So we can put all that together. So let's do that. So let's write down our node. We know that V2 is 15 volts greater than V3. So we add, all we're doing for V2 is V3 plus 15. That's because of this power supply right there. So that's where all that comes from. All right, so the first thing we're going to do is we're going to do it the algebraic method, and then I'm going to show you the matrix method. So depending on which, way you want to go about it. Again, this class is not going to emphasize doing matrix algebra as a requirement. I just find that it is a little bit easier to do since I have access to the calculation tools to do that. So that's the method that I usually use when computing these nodal equations. And eventually we'll get into mesh current and do the same thing. When I solve linear systems of equations, I use matrices. But at the same time, you can solve it using standard algebraic techniques. It's the same thing, same process. Just one takes a little bit more time, and it's easier to get lost along the way, as you're probably going to see here in a second. So let's just start by simplifying our equations. So we start with this, which is from our second equation. If we remember a moment ago where we combined the V2 minus V1, the I15 volts, well, this is that equation. Now, one thing you'll notice is these two basically the V2 minus V3, this and here will end up canceling out, but let's just go through and simplify that. So we just go ahead and expand things out, expand it out, and then cross out everything that cancels, and we end up with this. 6 V2 over 20 ohms minus V1 over 5 ohms equals 2 amps. Now we can solve our equations. So we have our first equation that we had from earlier, and then which is from node V1, and then we have node V2. So we now have 2 equations with 2 unknowns, which now we can simplify and solve one of them in terms of the other. So we're going to solve for V2 first in terms of V1, and then we're going to plug that in for V2, and then solve for V1. So V1 ends up being 3.5 over 0.85, which ends up being 4.18 volts. And then using this, in this equation here, we're able to solve for V2, ends up being 9.411 volts. And in V3, it's just simply take that and subtract 15 volts, and you can find V3. So the problem here is where you're going to have problems like in homework and on tests, you're going to be asked, what is the current flowing through R1? Or what is the voltage? What is the node voltage 1, 2, and 3? You know, node 1, 2, and 3. Well, you're being asked a specific thing. What is the, current or voltage across a resistor? What is the power going through a resistor? All of which is going to require you to solve for these node values and to then answer the next question, which is like what power is or something. And of course, now once we have these values, you would then verify using the equations that we have. So what you would do is you would plug this value in and this value in into both of your nodal equations, and you should get, with 7 times 4.18 volts divided by 10 ohms minus 9.411 volts divided by 5 ohms should equal 1 amp. Same thing here. We should be able to take this exact same formula again here for node V2, and I should get 2 amps. So you can take the answers you derive from your algebraic simplification and solving and verify that you get the right values. So what's going on here is you're taking the nodal voltage method and eventually the mesh current method, and you're deriving equations from that and then solving the equations for the values, and then you verify that the values are correct by plugging them in the original equations. So now we're going to solve this using linear algebra. So same problem, same nodal voltage equations, just now we're going to solve it using matrix algebra, just linear algebra. So let's take our two equations, node 1 and node 2. Obviously, I'm going to say here, I is equal to 15 volts, and then use the node 3 equation, plug the two together, and we end up with the known here of V2 is equal to V3 plus 15. Because in the end, we have actually 3 unknowns, V1, V2, V3, and of course the reference node being 0. So we have 3 unknowns, and we're going to need 3 equations to solve for 3 unknowns. So let's take that. So we combine this together, and these two again, this node 2 and node 3, combine together to get us this one equation. We saw this a moment ago. So again, this term here and this term here cancel out. So we end up with, if we do that, and we also take the node equation number 1 here, so if we take this node here, we plug in here, that's where those terms, so that is your 1/2, 0.5 plus 0.2, which would be this part here. These two parts here lead to the 0.7. Then this term here, 1/5, gives us the minus 0.2. There is no V3, so that's why that's 0. And then we have equation here for 2. We've got this one up here, which again, these two terms have canceled out. And we end up with minus 1/5. So we end up with the minus 0.2. Then we have this 0.3. Where did this come from? Now it comes from this part here and this part here. So 0.2 plus 0.1. So it gives us 0.3. And then using this equation down here is where we get this term. So we have 1V2 minus V3, so there's that, minus the V3, equal to 15 volts. So this is assuming, of course, X is V1, V2, V3, and the result vector, B, is 1 amp, 2 amps, and 15 volts. That's where all that comes from. So now we have 3 separate equations. And notice that the first 2 equations worked in amps and the last one worked in volts. It doesn't matter. I just need 3 equations representing my V1, V2, V3 relationships because I'm solving for X here. I'm solving for V1, V2, V3. So the equation to solve is X is equal to A inverse B. So now that I have A, I can get the inverse of it using MATLAB or my calculator, whatever tools. Don't really recommend for the class going through by hand on paper solving the inverse of the matrix A. Kind of would defeat the point of speeding this process up, because you might as well solve it by using standard algebraic methods. So you find A inverse, and multiply it by B, and you end up with V1, V2, V3 equal to 4.1176, 9.4118 volts, and then V3 minus 5.5882 volts, which again, you can verify by placing all of these values back into these equations and verifying that your answers match. So I'm just highlighting again, this is a very special case when you're doing this on the test. You're going to have a little bit of time so you can come up with these answers, and it just takes an extra 30 seconds to go and put these values back in your original equations, and then you'll know whether or not you got the problem right or wrong. So if you plug these values back in your original equation and say that was a 20-point part on the problem out of a 100-point test, then you got 20 points. You don't even have to worry about that problem. You got it. If these numbers match, if these numbers match these original equations and you got the answer, you're good to go. Unless there's something very fundamentally wrong, which I highly doubt at that point, because the only way that honestly all these equations can end up answering and balancing out is if you did the circuit analysis correctly. Now I'm going to briefly talk about this thing called supernodes. I really don't use this too often. This is a topic in the book. There may be a homework problem in here. I can tell you there is no test problem on this. This is just so that you understand what a supernode is. Again, I really don't use this very often in my circuit analysis. I usually just stick with the traditional nodal voltage and mass current analysis, which we're about to talk about. But all supernodes is talking about here is we can combine everything up and just kind of create one set of master equation over this. So obviously here we've got these two power supplies, this 15 volt here and this 10 volt here, which using nodal voltage methods complicates the math a little bit, because as you just saw in the example we just had, we had to create this I-15 volts. We had to create this separate term. Well, by using the supernode method, you could have skipped through that. So, and that's fine. And that's basically, if you look at what we're about to do, is basically exactly what we just did a moment ago. It just kind of does one of the steps is done just through analysis. So what it's saying is that the KCL still applies, but it's saying the net current flowing through any closed surface must equal 0. Instead of just the node, it's considering the surface. So what it is the surface here they drew around this 10 volt power supply, they drew a circle around V1 and V2. So what's being said is that the net current flowing out of here must equal 0. And then the same thing's true here, that the node that everything around here must equal 0. So the current coming out of this node must also equal 0. So that's all that's trying to say. Which, if you wrote the equation for this particular problem here, works out like this. So with V1, you still keep the same nodes. That's what makes this a little convoluted to think about. It's just basically combining a couple equations for you. So I'll just try to step through this slowly here. So we have V1 over R2. So again, if we draw our circle here, and we're just looking at what's flowing out. So we first got this current here, V1 R2. That's this current here. In fact, I'm just going to sort of kind of hash this right here, so we're not even, other than here, let me make it obvious a little bit. We care about the V1 and the V2 in the sense of the nomenclature for it, but we're just sort of getting rid of the 10 volt power supply out of the equation is what we're doing for this particular equation. So we have V1 over R2, and then we have this right here. We have V1 coming, so we got this current here. Well, what is this current? That's V1 minus 15. So it's still considering this node voltage. This node voltage is minus 15 volts simply by the fact that we've got ground here and we got minus 15 volts that's being generated because of the way this is hooked up. So V3 is by definition minus 15 volts. So let's just take a look at that. So again, keeping this little line, this current here, that is the V1 minus the minus 15 volts. So that's where that comes from, over R1, that right there. So we got that current and that current. And then we have this current here coming out of here. Again, let me just keep my master circle here, which is V2 over R4. And then we have this current here, which is V2 minus 15 again over R3. So all that must equal 0. So this is just a way of, effectively, we just got rid of this power supply in writing this one equation. Just gave us one equation in the end. Now we have now V1, V2, right? Everything's now in terms of V1 and V2 because V3 is known. So we have two unknowns, but only one equation, which means now we need another equation. Well, what do we know to do that? Well, we have V1 and V2, but we also have a relationship between V1 and V2 that is known. 10 volts. We know there's a power supply. V2 happens to be 10 volts greater than V1 because there's a power supply between the two. So that's a known. And it's written like this, but in the end, you could write it like this. You could easily say V2 is equal to V1 plus 10 volts. With that, now you have everything to solve this problem. We have two equations and we have two unknowns. So we have everything to solve for V1 and V2. So if you want to solve through this by arbitrarily choosing values of R1, 2, 3, and 4, go right ahead, but that's the general concept. In the end, we have two equations and two unknowns. So in summary, this method is used for solving the different voltages at different nodes in the circuit. Again, the purpose of the two methods we're learning here, which is nodal voltage method and mesh current analysis, which is going to be the next set of lectures, is to provide a straightforward, step-oriented process for solving a circuit. You do not have to go through and reduce resistors and come up with, equivalents here and equivalent there and accidentally drop something and make a mistake, which is common if you're trying to do circuit reduction. Nothing wrong with circuit reduction, but you can make mistakes in redrawing the circuit over and over again. So this method provides a straightforward, systematic way of analyzing a circuit. So that's what we introduced here. And of course, we also introduced the concept of solving linear equations using the matrix or linear algebra method, which is definitely going to be handy when you're starting to use, come up with equations of probably anything greater than 3. With equations with, we have two equations and two unknowns, it's not really any more complicated to solve, doing standard basic algebra, but I do find using the matrix solution kind of cleans up the math and provides an easy way of solving everything and coming up with an answer. And of course, it's supported on most calculators and platforms today. I would also say always check your answers. Whatever answer you get, go back and plug back into your original nodal analysis equations, and they should equal 0 in the case of nodal analysis. They should return and equal all of the sum of the currents entering a node or leaving a node should equal 0. So KCL should be applicable in your equation. So there's always a way of checking your